Welcome to the course Cssy4203 Malware Analysis and Reverse Engineering. This course teaches you how to study malicious software, understand how it works, and uncover the techniques attackers use. You'll learn to break down malware step by step, analyze its behavior, and apply reverse engineering skills to strengthen cybersecurity defenses. It's a hands-on journey that combines theory with practical labs, preparing you to detect, analyze, and counter real-world threats. By the end of the course, you'll be equipped with the tools and mindset needed to face modern cyber attacks with confidence. This course provides foundational knowledge in malware analysis and reverse engineering through the deep analysis of real cases and hands-on examinations of malware samples. The objectives are to enable students to identify different types of malware and their effects, examine malware using various tools, and avoid malicious software through modern techniques. Moving on to the course learning outcomes. Upon completion, students will be able to comprehend malicious software characteristics, synthesize cybersecurity challenges, examine malware to identify vulnerabilities, perform independent analysis of malware samples, and apply modern techniques to protect against malicious software attacks. Here are the graduate attributes covered in this course. The course fosters communication skills, teamwork and leadership, discipline knowledge and skills, creativity and innovation, entrepreneurial skills, lifelong learning, technical and digital competency, and critical thinking, analysis, and problem solving. The course coordinator is listed next. Week 1 and 2 covers Introduction to Malware Analysis and Reverse Engineering, including definition, classification, and tools, with hands-on labs and discussion. Weeks 3 to 4 focus on advanced assembly language concepts involving reviews of basic assembly language with corresponding lab exercises. In weeks 5 and 6, we'll cover basic static analysis techniques. This includes what static analysis is and why it's important, key methods such as file fingerprinting, string analysis, disassembly, and decompilation, and approaches to deal with packed or obfuscated malware. These topics will give you the foundation to analyze malware without executing it. Also, in week 7, we'll move into basic dynamic analysis. The focus will be on practical techniques, such as sandboxing, to safely observe malware behavior in a controlled environment, debugging tools and techniques, to step through code execution and uncover hidden actions, and memory analysis, which helps detect and understand malware activity during runtime. In weeks 8 and 9, we'll explore advanced static analysis techniques. The topics include control flow analysis and graphing, to visualize how code executes, data flow analysis, to track how information moves through a program, advanced code navigation and cross-referencing, for deeper inspection of complex malware, and automated pattern recognition, used to identify malware signatures efficiently. These advanced methods will strengthen your ability to analyze and detect sophisticated threats. In weeks 10 and 11, we'll focus on advanced dynamic analysis techniques. The topics include an introduction to kernel-level debugging, which allows deeper inspection of system-level malware behavior, analyzing network communications to understand how malware interacts with external servers, and memory forensics and heap analysis, which reveal hidden activity and data manipulation during runtime. These advanced methods will equip you with powerful tools to investigate and counter sophisticated malware. In weeks 11 and 12, we'll focus on malware functionality. You'll learn to understand common malware behaviors such as backdoors, which allow attackers hidden access, credential stealers, designed to capture sensitive information, persistence mechanisms that help malware survive system reboots, privilege escalation, used to gain higher system control, detecting and analyzing rootkits, which conceal malicious activity, and techniques like process injection and hook injection, used to manipulate legitimate processes. This module will help you recognize how malware operates in real-world scenarios. In week 13, we move into advanced malware analysis. You'll explore polymorphic and metamorphic malware, learning how attackers constantly change code to evade detection. We'll examine fileless malware, which hides in memory and leaves no traditional footprint. Next, you'll dive into hardware-level analysis, focusing on firmware and BIOS threats that operate below the operating system. Finally, we'll uncover advanced evasion techniques, the tricks malware uses to bypass even the most sophisticated defenses. This week is all about sharpening your skills to face the most complex and stealthy forms of malware. In week 14, we'll dive into two major areas: reversing cryptographic protocols, and defensive techniques. First, we'll explore how to reverse engineer encryption algorithms, analyze cryptographic protocols, and break custom encryption schemes. Then, we'll shift to defense, covering the fundamentals of cybersecurity defense, developing and implementing countermeasures, building malware detection signatures, and using automated threat intelligence analysis. We'll also look at emerging trends in reverse engineering and malware. This week brings together offensive and defensive perspectives, giving you a complete view of both how attacks work and how to counter them. In Week 15, we'll conclude the course with project presentations and review. This is your opportunity to showcase your work, apply the techniques you've learned throughout the semester, and reflect on the key concepts of malware analysis and reverse engineering. Next up are the lab activities. Lab activities include hands-on exercises with simple programs, creating a malware analysis machine, practical exercises with assembly language, and utilizing static and dynamic analysis tools such as IDA Pro, Ghidra, WinDBG, GDB, and Wireshark. Here is a list of reference books for the course. The main reference materials are shown on this slide. We will now discuss the assessment plan. In this course, your performance will be evaluated through several assessments. Practical Exam 1, 5 marks. Quiz, 5 marks. Midterm Exam, 20 marks. Project, 10 marks. Practical Exam, 10 marks. Final Exam, 50 marks. Altogether, these assessments make up 100 marks in total. Each activity is mapped to specific learning outcomes, ensuring a balance between practical skills, theoretical knowledge, and applied analysis. The grading scheme is detailed here. Review this slide for the minimum required marks for each grade level. This section covers the attendance policy. Please note the attendance requirements and consequences for non-compliance. Next, we address the academic integrity policy. Adherence to academic integrity is mandatory, and penalties for violations are clearly defined. The academic calendar outlines important dates for the semester. Key academic dates are listed for your planning.